a talk by Nicole Huffer about micro-electron diffraction, where she'll be talking about a method to determine the structure of small molecules, proteins, and materials. And I also want to mention we have our schedule set up for the rest of the month, the next couple of weeks. So next week we'll have Robert Williams giving a talk about a TM technique and what you can do with segmented detectors. After that, we'll be going into the FIB with Dan Huber, kind of understanding what you can do with the focused ion beam instrument, kind of looking below the surface of what you normally would with an SEM. And then on to X-ray diffraction with Hank, and trying to understand kind of what we can do there as well. Yeah, with today's talk, I mentioned is going to be by Nicole on MicroED. So she'll give an introduction to micro-electron diffraction and a few examples of it. Again, with these discussions, we want to have lots of questions, have it be more of a discussion than anything. So we've been limiting our talks to about 30 minutes so that we have plenty of times for up to half an hour afterwards for questions. You can see down in the bottom, the easiest way to ask questions to be answered at the end is to hit that Q&A button, type it in there, or you can also ask questions if you want a live response from one of the moderators, so probably myself, in the chat. And then if you have some really in-depth questions at the end, and the Q&A is not going to quite get there, you can click that raise hand button and we can unmute you and have actual conversation as well. And if you also have any other discussions, difficulties or anything, just put those in chat as well and we'll try and get you helped out with that. Anyway, I'll give the floor to Nicole for her talk today. Thanks, Nicole.
Hello, my name is Nicole Höfer. I have a PhD in structural biology using lipidic cubic phases to grow crystals of membrane proteins. And after my PhD, I worked in industry for 8 years as a senior scientist where I developed different products. I worked in protein conjugation, protein stabilization, and assay development. And since October of 2019, I'm a postdoc at CEMAS to set up the MicroED system. And on the right, you can see two of my children. So the resources at CEMAS that we have, CEMAS, as you might know, is currently closed due to COVID-19, but you can always schedule a one-on-one consultation with any one of us in the techniques that are listed on this slide. So feel free to either send an email to the instrument manager or contact us via cemas@osu.edu. So on this slide, you see the instrumentation that we have available at CEMAS. And today we're going to focus on the Glacios cryo-EM. Now, when you think of a cryo-electron microscope, you essentially think of 4 different techniques that you can use. One technique is called electron tomography, which uses the microscope in imaging mode, and you can look at whole cells or organelles. Now, the resolution for this technique is relatively low, but it gives you an insight into the whole cell. And Bin will be giving a seminar about this, about tomography in June. Now, 2 weeks ago, you heard a seminar by Yoshi about single particle reconstruction. Again, the microscope is used in imaging mode, and you're looking at isolated single particles. The resolution can be near atomic resolution, but you're working with relatively large complexes. Now, as you know, every electron microscope also has a diffraction button. And so if you switch into diffraction mode, you have 2 more techniques available to you. One of them is 2D electron crystallography, and the other one is micro-electron diffraction. Now for 2D electron crystallography, as the name implies, you use 2D crystals, and you can get structures to atomic resolution. Now, because it is so hard to grow 2D crystals, there are only relatively few structures available. On the other hand, in MicroED, we are able to use 3D crystals, and this is the talk of today's seminar. So where does MicroED fit in? The most prominent method to determine a protein structure is X-ray diffraction. And it's a wonderful method, and the majority of the protein structures that are out there come using this method. It has one bottleneck, which is that it requires relatively large crystals. So crystals at least in the micrometer range. And sometimes, for whatever reason, your protein just cannot form crystals of that size. Now, in this condition, you have two options. You could either do serial femtosecond crystallography using X-ray free electron lasers. The challenge here is there are only a few facilities available in the world. It's hard to get time, and then there are other challenges involved with this method too. Now, on the other hand, you could also do micro-Electron Diffraction. The advantage here is that essentially every major university has a microscopy center these days, and you can use your small crystals there. Now, the alternative in electron diffraction, there are alternative electron diffraction methods. One of them is rotation electron diffraction. Another one is precession-assisted electron diffraction. And these methods come more from the material sciences and are not so useful right now for protein structure determination because they require specialized software to process the data. Now, if we talk about micro-electron diffraction, as I already mentioned, you need a cryo-electron microscope. And the advantage is that you use a parallel beam of electrons that illuminates your crystal, and your crystal is located on a stage. And while you shine electrons onto your crystal, you rotate your stage in a continuous way, and you collect different diffraction patterns. This method, at least for proteins, has produced 74 structures that are published in the protein data bank. And these structures have been shown to have high resolution. So what is the real advantage of MicroED? Well, you only need to use sub-micrometer sized 3D crystals. You use a very low dose, about 1 electron per angstrom squared for a data set. You can collect your data at cryogenic temperatures. And the method is very similar to the rotation method that is used in X-ray crystallography. And so all of the software that has been developed in this method can be used for MicroED also. So next, I would like to talk about the basic MicroED workflow. You begin with the sample preparation, followed by data collection and then data processing. Now, for sample preparation, there are 2 steps involved. One is crystal preparation, and the second one is TEM grid preparation. So, crystal preparation. Ideally, you would like to have a crystal that has an approximate thickness of 100 nanometers. So the challenge is there are really 2 challenges here. One is you need microcrystals, and the second one is you need to remove the precipitant solution. Now, how do you get microcrystals? On the one hand, very often dismissed by protein crystallographers, you can use what X-ray protein crystallographers would dismiss as precipitate. So you can use suboptimal crystals that are shown in the pictures A, B, C, and D. So needles, like tiny crystals, they're very useful for MicroED. On the other hand, if you have larger crystals, you can fragment them. So you can use sonication, vigorous pipetting, vortexing, or manual crushing to get your crystals down to a very small size. And there is a third technique called cryofib milling, which is emerging in this field. And you can essentially use a gallium ion beam to machine your crystal down to the size that you would like. So it gives you the opportunity to remove precipitant solution that you could not remove by blotting, and you can machine your crystal to the right size. But again, this is an emerging technique, and so it's in its infancy right now. But to summarize this, you can grow your crystals in any condition, hanging drop, sitting drop, under oil, LCP, essentially whatever you want. But that brings you to the next challenge, which is the TEM grid preparation. Now, what you need here, so you start by glow discharging your TEM grid that makes your TEM grid hydrophilic. Then you apply 4 microliters of your nanocrystal solution. You really need to determine this during your experiment, how much you need to apply. And then you remove the excess liquid by blotting, either using a Vitrobot, or you can remove the excess liquid manually. Now, what you want here is you want to remove so much liquid that the electron beam can penetrate your TEM grid. On the other hand, you want to keep your crystals, and that can be a challenging task. Now, once you remove the excess liquid, you freeze your crystal in liquid ethane, and then you store your TEM grid in liquid nitrogen. This area is an active field of development, and we're expecting that there are many new methods coming out within the next 2 years. Once you have your TEM grid frozen in liquid nitrogen, you transfer it into the electron microscope, and you can begin your data collection. At first, you need to identify nanocrystals, and this is then followed by testing the diffraction of a chosen crystal, followed by collection of a data set. Now, how do you identify a nanocrystal? Initially, you screen your grid at a low magnification to identify promising areas. That is kind of shown in the lower picture here, labeled with search mode. Once you find an area or a grid area of interest, you increase the magnification, and you kind of look at the crystal of your interest. Once you find that crystal, and examples of crystals are shown in the picture labeled with E, F, G, and H. Once you find that crystal that you like, you take a first diffraction pattern, and you look at the resolution and at the quality of the reflection spots. You want them to be sharp and well separated single spots. Now, if your crystal satisfies those conditions, you can begin to collect the data set. Now, you have to remember that because it is a microscope, the tilt range is limited from -70 to +70. So the maximum number of degrees you can collect is 141. So you rarely ever use that. The challenge is because often radiation damage limits your data collection. What you have to do is you have to collect several data sets from different crystals, and then you merge them. Now, a good starting point to collect data for proteins is to use a frame rotation of 0.5 to 1 degree, and for small molecules and peptides of 1 degree to 2 degrees. Now, here I would like to mention that it is really useful with the continuous rotation enables you to collect complete intensities of your diffraction spots. That's an advantage over other electron diffraction techniques. So once you have collected several data sets, you move on to indexing, integration, merging of diffraction data, then the phasing of your structure, and the refinement of your model. So here I would just like to show you the basic setup of the diffraction experiment. We have the electron beam that went into your crystal, and then we have the diffracted beam from your crystal with the electrons that hit your detector. Now, one challenge is you do not know the orientation of the reciprocal lattice of the crystal in relationship to the laboratory coordinate system or the detector coordinate system. And in order to get the indexing to work, you need to bring all of the information that you have together. So what you do is you have your set of diffraction frames. These diffraction frames have positions of reflections recorded on them. And parameters that you know about your experiment are, for example, sample detector distance or the wavelengths that you used. Other parameters that are unknown, as I already said, is the orientation of the crystal relative to the lab coordinates. Now, from this information, you need to extract the primitive lattice basis. And on this slide, I would like to show you how this is usually done. So you usually use a list of very strong diffraction spots. And what you do is labeled with S0, that's the incoming wave vector, and then labeled with S, and that is the diffracted wave vector. And they differ by the reciprocal lattice vector P. And the reciprocal lattice vector P consists of the basis lattice vectors B1, B2, and B3. And they're weighted by the integer values h, k, and l. So a choice of h, k, and l determines the change in wave vector, and therefore where the diffraction spot will appear. And once you know that, you know the orientation of your crystal, and you can also identify the symmetry of your crystal. Now, at this point, I would like to mention something. When we use electron diffraction, and we use, for example, the glaciers, we work at 200 kilovolts. And that gives you a wavelength of 0.025 angstroms. Now, compared to X-rays that are generated on a copper anode, have a wavelength of 1.54 angstroms. So you notice that the wavelengths we're using is significantly smaller in electron diffraction. If you remember from your crystallography, the Ewald sphere, the size of the Ewald sphere is determined by the wavelengths. Now, in MicroED, because the wavelengths are so small, the Ewald sphere is so large that at the edges, it appears almost flat. And this is kind of described in the picture here. So you see the red line indicates the Ewald sphere. It's flat in electron diffraction, where it is curved in X-ray diffraction. So in X-ray diffraction, you would get the planes L0, L1, L2, whereas in electron diffraction, you might only get the L0 plane. And this can be a challenge for some of the indexing programs. But we're going to assume our indexing was successful, and we're ready now for the integration and scaling. So data integration really just means the process of estimating or measuring the diffracted intensities. And once we have the intensities, we essentially now have a list of h, k, and l values with a standard error and an intensity. And some of those reflections may appear a couple of times in our data set so far. So since they're the same reflections, we can bring them together in a process called scaling. So in the scaling process, we bring the reflections onto a common scale. Now, once we have that, we can move on and phase the structure. So in order to generate a density map into which an atomic model is built, both the structure factor amplitudes and the phases are required. Now, the amplitudes are proportional to the square root of the reflection intensities, but due to our experiment, we lost the phase information. But there are methods that have been developed that we can use. One of them is molecular replacement. So in the case of protein, we would use a homologous structure and see if we can get initial phases. For small molecules or molecules that have very high resolution, 1.2 angstroms or better, we can also use direct methods in which we estimate the phases. And then recently, there was a publication by the Gonen lab that used radiation-induced phasing to determine the phase of your structure. Once you have your phases, you can move on into refinement. Programs that you use there is Phoenix Refine or RefMech. Those programs offer an electron scattering factors that improve the quality of the resulting density map. And always keep in mind that you're working with a Coulomb potential rather with electron density. So once you have your structure is refined, you can extract the information from it. Now, I would like to give you an overview of the potential applications. So there are applications in material sciences and in life sciences. So in the life sciences, we think about proteins, prions, small molecules, and in material sciences, it's minerals, functional materials, aperiodic materials, zeolites. So as I already mentioned, in the life sciences, there are 74 published structures in the protein data bank. The method MicroED gained a lot of attention with the breakthrough resolution of a peptide alpha-synuclein that had a resolution to 1.4 angstroms. Since then, there have been numerous peptides and proteins that have where the structure was determined, and the method has helped insights into diseases like Alzheimer's, where other methods like X-ray crystallography could not be of use because the crystals could not be grown to an appropriate size. Now, I think every lab or every X-ray crystallography lab has crystals that they could never get to grow. So if you happen to know someone with crystals like that, just let them know and they can contact us and maybe we can help them. Oops. The next example are small molecules, pharmaceuticals, and natural products. Now here, the advantage of MicroED really is the easy sample preparation. And that is shown in the picture on the right side. You can see the powder, in this case, it's progesterone. What you do is you take your powder, you essentially just dip your TEM grid into it. And that, once you dip it in, will have enough nanocrystals on your TEM grid that you can take that to the electron microscope and you can start a diffraction experiment. You can collect the data set and then you can solve the structure of your small molecule. So what you see from that is that you really only need very small amounts of material. The Golden group has shown that you can also identify a mixture of different materials or of different components in your sample. You don't need to grow large crystals anymore. And once you have synthesized material, you can directly apply it to the TEM grid and analyze it. So it's going to be a wonderful method for small molecules. And then I would like to end my talk with some applications in material science. So on the right side, you see a gold microcluster that had a resolution of 0.85 angstroms. There are also zeolite crystals that are now, or structures of zeolites available that diffracted to 0.8 to 1 angstrom. And no other method was able to solve this structure. So in material sciences, you can use it for nanoparticles, metal clusters, zeolites, functional materials, minerals, aperiodic materials. So I would like to thank you for your attention. And if you're interested in a collaboration, please contact me under hofer.3@osu.edu. And on the following slide, you can see the upcoming presentations. Thank you very much.